Okay, hello everyone. So in this video, we're asked to prove that the language 0n, 1j, where n is strictly greater than j, and j is greater or equal to 0, is not regular. So here, for the sake of simplicity, we're also assuming, of course, that the alphabet is 0, 1. Okay, and so here to do this, we're going to just use a classic pumping lemma proof. So we're going to prove this via the pumping lemma, by the pumping lemma. So how does a pumping lemma work? Well, we have an opponent. Our opponent picks some integer m, where m is strictly positive. Okay. And based on this choice of our opponent, now what we need to do is we need to choose w in L, where w has length at least m. So remember, w has to be a particular string in the language L, right? So it has to satisfy this condition where the number of zeros has to be strictly greater than the number of ones. Well, in this case, what I'm going to pick is what I want to do, right? The intuition is I want to pick so that the decomposition that my opponent uses is somewhat constrained, right? So they have a limited amount of choices to do. And so usually how that works out is that you want the m first letters in the string to be of the same symbol, right? So that you can identify the string y as only containing symbols that are in that sequence, okay? So that helps you out because then for any decomposition, you know that y is just going to be composed of a single symbol, and then pumping up or down, you know exactly what the form of the pumped string will be. And so in that case, what we want to do is we want at least w to be, say, 0m, 1m. Okay, this is typically one of the canonical examples of pumping lemma, right? So this was the string that we picked for 0n, 1n. But now in this case, we need the number of zeros to be strictly greater than the number of ones. And so to do that, what we can do is we can just add, excuse me, we can just add an extra 1 to the number of zeros, okay? And you're going to see in a second why this actually matters, why it couldn't have been m plus 7, let's say, okay? So we pick the string w. Now our opponent decomposes w into x, y, z. And so here, because xy has to have length at most m, and y has to have length at least 1, right? This together implies that y has to be k number of zeros, right? Because it has to be within, so if I have my string here, let's use purple. So this is my string. I have m plus 1 zeros, and I have m ones. Now, because xy is at most until the before last zero, that means that the y here is just a sequence of zeros, right? So y is equal to 0k. That's a safe sort of assumption about the decomposition. Well, it's a safe implication about what the decomposition must be. So my opponent decomposes their string, and we know that however they decompose it, we're going to get y is equal to 0k, where k from this condition has to be at least 1 and will be at most m, right? Okay, and now we need to pump. So we need to choose I. Well, here we can't choose I greater or equal to 2. So we cannot pick I greater or equal to 2 because that would just be adding more zeros to the zero part of my string, right? So you would be just, by pumping up, you would be adding more zeros. But then if you add more zeros, you're just increasing the number of zeros here. So if you increase the number of zeros, then n just becomes bigger and bigger, and you don't get a contradiction because the initial string already had number of zeros strictly greater than number of ones. If you add to n, then this equality, or this inequality rather, will still hold, and so you won't get a contradiction, or you won't get the pump string not in L. And so what that tells us is that the only way to pump in this case is that you must pick I is equal to 0, right? So in other words, if you have W, which is X, Y, and Z, Z is 0 Ks, or K zeros, then what you need to do is you need to compute W0, right? W0 is X, Y0, Z, which is just X, empty string Z, which is just XZ, right? So in other words, what you need to do is you need to cut out the string Y, right? So from the initial n plus 1 zeros, right? So from the initial, so in your initial string, let's say this was W1, in your initial string you had n plus 1 zeros, and now you're taking away K zeros because that's how many zeros are in Y. And so you take away K zeros. And then the number of ones stays the same. Now, why does this not belong to L, right? So my claim is that now we have something that does not belong to L. Well, that's because m plus 1 minus k, right? So you have m plus 1 minus something that's at least 1, right? So k is at least 1. So it could be more, but you know that it's at least 1. And so at most, right, at most m plus 1 minus k, right, you have m plus 1 and you're taking away k. You know that k is at least 1. So in the at most case, right, in the upper bound, m plus 1 could have only 1 taken away from it. And so m plus 1 minus k would be at most m, right? It could be less, right? It could be m minus 2, it could be m minus 5, right? It could be half of m, but you know that the best case for your opponent really is if you take away the least amount as possible, because your opponent wants to fool you, right? So in the best case for the opponent, that would be that the number of zeros still stays above the number of ones. But here we see that for any I, right, so, for any k, because we know that k is at least 1, we know that that's never going to happen. We know that m plus 1 minus k is going to be at most m, right? And so that means that you'll have 0 something, 1 something, and here the number of zeros in W is going to be at most the number of ones in W. Okay, and so that's clearly a contradiction because here what L requires, it requires that the number of zeros must be strictly greater than the number of ones, right? And so indeed that means that the pumped string here, W0, is not in L, and so we therefore have proved, right? Therefore, L is not regular. And so the reason why it was important for us to pick, in this case here, plus 1 and not plus 7, for instance, right, just to pick some number. So, because if we had picked plus 7 here, if we had m plus 1, instead of m plus 1, we had m plus 7, then m plus 7 minus k is not guaranteed to be at most m. And so we care about this m because that's the number of ones we have here, right? We want the number of zeros to be at most the number of ones so that the pumped string is no longer an L. But here we can't guarantee that if m plus 7, if we have m plus 7 minus k, because in this case, if k is, for example, 3, then we have m plus 4, right? And m plus 4 is still strictly greater than m. So in that case, we get that the pump string is still in the language. And so that means that our opponent could, if they're clever enough, pick a decomposition that fools us. And it fools us because we incorrectly picked the string W, okay? And so that's why the +1 instead of the +7 is crucial here, okay? The other thing that's crucial is to recognize that you have to pump down and that you can't pump up. Okay, so that's an example about using the pumping lemma to prove that a language is not regular.